Percentage composition is one of the primary numbers that we would give to a compound, especially if we're trying to determine what a chemical formula is. Now, this by itself is going to seem like just something that we can do to a chemical formula. It's not some math that we can apply. But in reality, if we're trying to find the chemical formula for a compound, one of the things that we would want to know is the percentage composition. I don't know if you've ever looked at, like, when you get a medicine, a drug from CVS or whatever pharmacy you go to, they give you some documentation that comes with it. And a lot of times if you buy a box of something and it comes with an insert in the box, if you open that up and look at it, real tiny little print, you'll find a percentage composition for whatever drug that you have. You'll also find something called an empirical formula, which we're going to go about how to calculate empirical formulas also. All that information is necessary to come up with a chemical formula from laboratory data, not from oxidation numbers and crisscrossing oxidation numbers to get the charge right, but specifically from collecting data in lab and determining the chemical formula in that way. So percentage composition, according to our definition here, is the percentage by mass of each element in a compound. And when we calculate this, an important law that comes into play here is the law of definite composition, formulated by Proust in the 1800s. And this states that a chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size or source of the compound. So what this means is percent composition is constant for a compound. It also means, besides that the chemical formula is always constant. So if the formula is constant, then the percentage composition also has to be constant, and that makes it such that, first of all, it makes it so that we can always write a chemical formula and always use the same formula for the same substance, but it also allows us to analyze chemical formulas, and once we've done the analysis, we know the composition of the compound, and we can expect that compound to always contain that same composition, no matter where we get it from. So water, for instance, is always H2O, and it always has the same percentage hydrogen and same percentage oxygen by mass, regardless of where it comes from. It doesn't matter if it's produced in a chemical reaction or if we take it out of a distilled water bottle. The end result is that water is going to have the same formula and same composition always. So that makes it a very useful analytical value. If for nothing else, if we have an unknown compound and we suspect that it might be something, then we can analyze the composition and see if it matches what it's supposed to. If we think it's glucose, for instance, C6H12O6, we can analyze the carbon, hydrogen, and oxygen content, and if it matches glucose's content, that's a piece of evidence, at least, that it is glucose. If it doesn't match, then it's not glucose. So we can use it to identify unknowns as well as just finding out basic information. Okay, let's see how this is done. We're going to find the percentage composition of copper 1 sulfide. Copper 1 sulfide is copper with a positive 1, sulfide with a negative 2. So when we form the formula for this, we're doing this from the chemical formula. We would have Cu2S. All right, so if we want to know the percentage composition, if a problem is phrased this way, and it doesn't say like the percentage of copper or percentage of sulfur, then you find the percent copper, and you also find the percent sulfur, or every element in the compound. If there are 5 elements, you find the percentage of all 5. To get this, if we want to know the mass of the percentage of copper in the compound by mass, we need to know the mass of copper in the compound divided by the total mass of the compound. And then what do we do to this to convert it to a percentage? Multiply by 100. Because really what a percentage is you could call it a parts per 100. It's the number of parts of copper per 100 parts of copper 1 sulfide. Okay, so looking at this, we've got how many moles of copper are showing in this compound. How many? 2. How many moles of sulfur? 1. So what we would have here is we would have, I'm going to erase this. I'm going to do a little more on the copper than I would on the others. We would say that we would have the mass of 2 moles copper over the molar mass of Cu2S. Okay? And that's going to give us our percentage of Cu. Notice that we can use the mass of the copper 2 sulfide from the periodic table as our total mass. We don't have to have a sample. We can just use 1 mole worth. Because it doesn't matter the size of the sample, according to the law of definite composition, the percentage is going to be the same no matter what mass of sample that you have. Okay, so percent of copper then is going to equal, we've got 2 moles multiplied by the mass of 1 mole of copper, which is 63.5 grams. So this is the mass of copper. And then this is going to be divided by the total mass of the compound copper 2 sulfide. So let's do that calculation. Let's find out the mass of copper 2 sulfide. Okay, so we've got 2 coppers. So that's going to be 2 times this. Gives up a little more room. 2 moles copper times 63.5 grams of copper. And then we've also got 1 mole of sulfur times 32.1 grams per 1 mole of sulfur. Where's the 63.5 and 32.1 coming from? Periodic table. So 63.5 times 2 is going to be 127. And then this is 1 times 32.1 is 32.1 grams. So that's going to give a total of 159.1. Okay, so that's our mass of the total compound. So that's going to go in the denominator as the molar mass of copper 2 sulfide, 159.1 grams. And then this ratio times 100. So as we do this division, 2 times 63.5, and then divide by 159.1, multiplied by 100, that gives 79.8% copper. That's one of our answers. We still have sulfur to do, but less calculation to do with sulfur because we've already done the bulk of it. Okay, questions here, where anything came from? When I do this 2 times 63.5, what am I finding? I'm finding the mass of 2 moles of copper. This 159 is the mass of 2 moles of copper plus 1 mole of sulfur, 159.1. So how do we get percentage sulfur? We need the mass of 1 mole of sulfur, which is 32.1 grams of sulfur. And what do we divide that by? Total mass of the compound, which is 159.1 grams. So once we get this bottom number, we have a lot less to do because we use it the same in the same location in the next problem. Times 100. 32.1 divided by 159.1. gives 20.2. What's your check to see if you've done the correct calculations?
How'd you get the number at the bottom?
Add those two together, and if you add 79.8 and 20.2, what do you get? Sum is 100%. What's that number?
How'd you get the number? Yeah, right
The 159.1?
here. Yeah.
Find the molar mass of the compound like we did yesterday.
Okay.
So 2 times 63.5 plus 32.1. Okay, but these two have to add to 100. Now, suppose we did this. Suppose we found 79.8% copper, and then we said 100 minus 79.8 gives 20.2. Is that a safe method? What are you assuming about your first answer if you do that?
It's correct.
You're assuming it's correct. And you're always going to end up with 100% if you do that, so you lose your checking system. So it's best to do the individual percentages and then add them to see if they come to 100%. Do you think there's any reason for it to come up to a little above or a little less than? And I mean by like 0.01 above or below. Possibly because of rounding. So if you round each problem, you might not get exactly 100.000%, but you should be very close. Okay, questions about where any of these numbers are coming from? A lot of numbers there. All right. Let's try another one. We want to find the percentage composition of lead 2 chloride. So lead 2 chloride. Lead 2 is lead with a positive 2 charge. Chloride is Cl with a negative 1 charge. So this formula is going to be PbCl2. All right. One thing that we're going to need to know, that we know we're going to have, is the total mass of the compound. So this is going to be 1 mole of lead times the molar mass of lead is going to give grams due to Pb. And then we're going to have 2 moles of chloride the chloride we're going to convert to grams, and then that's going to give us grams of Cl. So with our molar masses, lead is 207 grams in every 1 mole of lead. Chloride, 35.5 grams for every 1 mole. So this is going to be 207 grams, because 1 times 207 is 207. 2 times 35.5 is 71.0 grams. That's going to add to 278.0 grams. Where? Here? Mole. Yes. So from there, we were looking to find the percentage composition of lead 2 chloride. So we have the whole mass. Now, one thing that you may have heard somewhere along the way in finding percentages is that a percentage is a part that you're interested in divided by a whole times 100. Okay, the part we're interested in first is lead. So percent lead, the part we're interested in is mass of lead divided by the whole, which is the mass of PbCl2, and then we multiply that ratio by 100. Okay, so according to our formula, which is PbCl2, we've got 1 mole worth of lead. So 1 mole worth of lead, we've actually already done the calculation up here, is 207 grams. Then that's divided by the mass of the whole, which is 278. And then that's going to be multiplied by 100. And you can see lead takes up the majority of this mass, 207 278ths. And that's going to come up to 74.4%.
I guess, can we round it?
0.5. Yeah, it should be 0.5. There's a 6 following that 4. Okay, so that takes care of the lead. Then our percentage of chloride is going to be the mass of chloride that we had in the compound, which is here, 71 grams.
Oh, so we don't have to rerun it out like we did the previous one?
Yeah, I think we can simplify.
All right, cool.
71.0 grams, and that would be of chloride, divided by the same whole mass, 278, times 100. So that's 71 divided by 278. And multiplied by 100 is 25.5%. Actually, 25.5%. Okay. That comes up to, hold on a second. So we add those two numbers together, we would expect 100%. Add them together and you get 100.1%. And of course you would want to check. I have rounded 71, 71.0. Actually I rounded chloride to 35.5. So that's a rounded value. And the lead is also slightly rounded. And I've rounded at each step of the calculation as well. 74.6 versus 20 and the 25.5 are both rounded values. So this is an acceptable value, 100.1%. Okay. You would hope, of course, that it would be exactly 100, but in this case it wasn't, again, due to rounding. Okay. Questions? Everybody finished with that slide? Okay. I'll let you try one. But let's start by getting the formula. Percentage composition of barium nitrate. Barium, positive 2 charge, nitrate, negative 1 charge. So the formula should be Ba1 NO3 2. So find percentage barium, percent nitrogen, and percent oxygen. All right, so the first thing that we want to do, we're interested in the part divided by the whole. These are the individual parts that we're interested in, barium, nitrogen, and oxygen, but we've got to find the whole mass. We need to know the mass that barium is a part of, that nitrogen is a part of, and that oxygen is a part of. To get that, we have to sum the masses of all of the moles of atoms that we have here. We have 1 mole of barium. You can see that because we have a subscript of 1. We have 2 moles of nitrogen because the 2 multiplies through the parentheses. So that's 2 moles nitrogen. And we have 6 moles of oxygen. Okay. So to find the number of moles of barium, we would say that there are 137 grams in every 1 mole, specifically of barium. This 137 is coming from the periodic table, rounded to 3 significant digits. The nitrogen is going to be 28, it is not, it is 14 grams for every 1 mole of nitrogen, again from the periodic table. And our oxygen rounded to 3 significant digits, is 16 grams for every 1 mole. So then we do the multiplication. That gives 1 times 137, 137 grams, with moles canceling. We have 2 times 14 is 28 grams, moles canceling. And 6 times 16, 96 grams, again with moles canceling. Then we find the sum of those values.
Wait, why'd you do 6 moles? I thought it was 3 moles.
2 times 3. Okay, so that gives us 137 plus 28 plus 96. That comes to 261 grams. So this is our whole part. We then find the percentage of the individual parts. So we start with percent barium. That means we need the mass of barium as represented by the chemical formula. We only have 1 mole. So we actually have all the numbers that we need right here in this section. We're going to take the mass of barium, 137, here, and we're going to divide by the whole, 261, times 100. Our percent of nitrogen is going to equal the parts of nitrogen that we have, 28 grams, divided by the whole, 261, times 100. And then finally we would have the parts of oxygen. So our percentage of oxygen, 96 grams, divided by 261 times 100. Yes, I put 216, didn't I? Okay, let me erase that. Thank you for spotting that. $261. And that is grams. Okay, so for the barium, we've got 137 divided by 261. And then we're multiplying by 100. That's going to be 52.5%. Nitrogen, quite a bit less. 28 divided by 261. That's going to be 10.7%. And then we've got oxygen, 96 grams divided by 261 is going to be 36.8%. And if you add those 3 together, you do get 100%. Okay, so what would happen if, for instance, you wrote the formula BaNO3, forgot the parentheses and the 2? What number would be off? Well, barium would still be okay. Oxygen would be off, nitrogen would be off, and the total would be off. You could still get percentages, and your percentages would still come to 100 if you did the calculations correctly, but the problem is the percentages would not match these. These percentages are specifically for BaNO3, 2, no other compound. All right, let's take a look at a hydrate. All right, we want to know the percentage composition of water, specifically in zinc sulfate, heptahydrate. What does hepta mean? 7. Okay, so formula for a hydrate, which we've covered, but we haven't seen in a few days since we had our break. zinc sulfate. Zinc is positive 2, sulfate's negative 2, so ZnSO4. And then heptahydrate we write with a .7H2O. So what we're interested in, the part we're interested in, is percent H2O. So our mass H2O equals the part. The mass of ZnSO4.7H2O equals the whole. And we have not added up a total hydrate at this point, so that's something new. All right, so let's begin by finding the total mass of zinc sulfate heptahydrate. Okay, we have, according to this formula, how many moles of zinc? 1. So we have 1 mole of zinc times the mass of zinc per mole of zinc. Zinc is 65.4 grams.
Yeah.
Okay, and that's 1 mole. We've got 1 mole of sulfur. This is zinc. 1 mole of sulfur. Sulfur has a mass of 32.1 grams for every 1 mole. We've got oxygen. How many moles of oxygen do we have? 4. That's times 16 grams for every 1 mole. And then water. We don't have to do hydrogen and oxygen separately. If we wanted to know the percentage of hydrogen there, then we would have to do hydrogen separately. But we're interested in water, so we can really just say 7 times water's mass. But here, in reality, since we're getting the total mass, it's probably going to be easier to say the number of moles of hydrogen and the number of moles of oxygen. So I'll reverse statement on that. How many moles of hydrogen do we have? 14 moles of hydrogen. And that's going to be 1.01 grams for every 1 mole. And how many moles of oxygen do we have? 7. So 7 moles oxygen at 16.0 grams per mole. Now notice that I've got oxygen 2 places. It doesn't matter if they're in 2 places. We're going to sum it all together in the end anyway. All right, so let's knock out the calculations. We've got, this one's easy, it's times 1, 65.4 grams. This one's 1 grams. 4 moles of oxygen, 16 times 4 would be 64 grams. 14 times 1.01, I think, is 14.14, but let me check myself. 14.14 is correct. And then it's going to be 112 grams. Okay. All right. Then what do we have to do? Add them all up. So we have 65.4, 32.1, 64, 14.14, and 112. That gives 287.6. So this is the sum, and that equals the whole. And we also have, you'll notice, except we almost have all the parts, except really what we're interested in is water, right? So we're not interested in hydrogen and oxygen being separate. So how can we get the mass of water that's in this compound? We can add up the 2 parts that came from water. Okay, so the part and that's going to be 14.14 plus 112, and that's going to be 226.14. I mean 126.14 grams. All right, so at that point we've got the part, we've got the whole, and it's just a matter of substituting. So we've got 126.14 grams divided by the whole, which is 287.6 grams, times 100. And that gives, looks like 43.9 percent H2O. What do you think would happen if you heated this compound? Zinc sulfate and water attached to the crystals. It would not likely blow up. Turn this off.